Morning, guys. So yesterday we had another look at our circuits. We know typical circuits have four main circuit elements. One is a source of the voltage, so typically the battery. We have a conductor that connects the positive and the negative. We think current is a flow of positive charges from positive to negative, even though reality electrons are actually going in the opposite direction. We have what's called the load, which is a resistance, which transfers that electrical energy of charges passing by into your light energy to power your light bulbs. Your load would actually be a resistance. We talked about what resistance depends on in yesterday's lesson. And as well, just to be environmental, we typically throw on a switch so that, especially when we're not needing the circuit, we're actually just able to flip the switch. I'm going to just introduce you to those two keywords here. As you connect circuits here, we can have what's referred to as a series circuit. A series here means everything is in one path. If you are there's only one way to get around from one side to the other side. We'll analyze this a little bit more here. For a series circuit here, I'm going to start off with the battery. Basically, there is only one pathway around. There's any number of resistors before I get back to the battery. Any current that flows from the positive end through the negative end, you're going to have to run through the first rough patch and run through the second rough patch here. We found that the formula for series, when we wanted that total equivalent resistance, well, because I'm having to run through every single rough patch, the R total, or the equivalent resistance, let me give you that name there, sometimes we call it REQ. If I want to swap out this combination for just a single resistor that does the same effect, we had derived it in the first lesson here. R total is equal to R1 plus R2. If I had more resistors, I definitely just go plus R dot dot dot. So that was the formula for series. Yesterday, we also introduced to us parallel. Parallel actually implied we actually had multiple circuits. Parallel. So we actually have multiple paths. In this case here, we had ended off last day saying, well, the more paths you have, well, the more options you're going to have. Overall, having a parallel pathway, it actually helps lower the overall resistance. So if I imagine drawing a parallel circuit here, maybe I have three paths, or it really doesn't matter how many. Each of these paths by themselves is R1, R2, and R3. We derive from Kirchhoff's loop rule, basically the total resistance for a parallel circuit. You notice the formula is different depending on whether we're looking at a series part or a parallel part. It was this reciprocal nature here, 1 over R total in this question, like we did yesterday, 1 over R1 plus 1 over R2 plus 1 over R3. If I had more, I'd keep going plus 1 over R dot dot dot. Okay. But just to show you, those are our two main designs here. Yes, definitely you can have a circuit that's, oh, this part here is actually series, the other part here is actually parallel, and then depending on which part that I'm looking at, I'm going to do the appropriate formula. In the olden days here, when we designed Christmas lights, we actually designed them sort of not really cleverly in series. You can imagine here, great, I plug this here into a wall, although the wall itself would be an AC voltage, sort of similar to the battery here. The light bulbs can actually steal some of the energy and actually shine bright. So great, we have the two light bulbs shining bright, no problem, and then one of the light bulbs here actually burns out. If you look at the actual light bulb itself, what's actually happening here is the current is actually going to the one side of the light bulb, leaving the other side. Inside the light bulb is actually a very thin tungsten wire. And what usually happens here when you have a burnt out lamp, usually, well, we know light bulbs themselves get really hot. Usually it's too hot that the tungsten wiring here, actually the tungsten actually snaps. The wire actually breaks. It's as if I've actually cut off the circuit. So in this case here, I was running my two Christmas light bulbs here and I end up realizing, this light bulb here breaks the circuit. It's as if you take a scissor. I'm not asking you to do this, but it's like taking a scissors here and cutting the wiring. Now that there's no complete path from positive to negative, this will no longer light anymore. Not only is this bad here, so I might have a burnt out lamp. That lamp is broken. Once this lamp dies off, the entire circuit cancels out. We're actually going to have this lamp here was actually working, but because there is no flow of circuit anymore, this lamp here will also go off. So the trouble here with Christmas lights, by designing in series, when one light bulb goes out, all the light bulbs are going to go out. You probably know intuitively it's probably not all the light bulbs burned all at once. That's too convenient. It's probably maybe one or two of them. But because all of them would now be off, it's impossible for you to actually figure out, well, which one is actually the one that's off. Nowadays, we design a little bit more cleverly here. Although the Christmas lights here, although when you pull the wiring, it might look like here's the plug on one end, and then we have our light bulbs on the other end here. Although it might look like one strand like that, we actually work the wiring so that it's actually parallel. The one way down the resistor is for the first light bulb, and then it's the other pathway here for the second light bulb here, so that every pathway here has its own independent source of voltage. Now we know the charges that go down one resistor here might not go down the other pathways, but the advantage here is that same story. Light bulbs inevitably do burn out. So let's say one light bulb burns out. It's going to show me which pathway is not available. It's going to cut off that potential pathway. If I cut off that circuit though, you'll see as long as my light bulbs are still plugged in, I still have a complete circuit that I can still go through R1, I can still go through R3. Not only does it solve my problem that most of my light bulbs will still be on, it's actually going to show me, oh, only this one here is off. That's the one I need to screw out, and then I put in replacement. So by designing in parallel, it's a little bit easier and a little bit more convenient. And again, what's tempting here is I know that the wiring from the socket, it looks like a one strand here. They can interweave however many number of wires, and they can play around with what is actual circuitry behind these light bulbs so that it actually does end up as parallel. One note as we're looking at that plug here, in the olden days, if I look at sort of the ending of a plug here, for the plug itself, definitely it's plugged into the wall. So this one here is going to take AC current from the wall. Basically what's going to happen here is you're going to have a positive side and negative side. That's almost like the terminals of the battery, like the positive and negative. Again, AC is a slightly different beast. But we have a positive and negative there. There's an electrical voltage stepping in between. Sometimes if you pull out the plug too quickly, we're going to find that nature always likes status quo. It doesn't like change. So if your light bulb here was on, the plug is in, everything's happy, as you pull out the plug itself, it's going to try, it knows eventually it's going to be off, but it's going to try to even jump the gap from the plug to the socket itself, just to try to continue that circuit just ever so slightly a little bit longer. So there's that case there. Nowadays here, instead of designing the positive and negative here with even sides, sometimes they actually make the positive prong a little bit larger than the other one. That way you know which is the positive side. The wall sockets themselves will also have one positive side, one negative side, so you can fit it in nicely. You'll also find that for some plugs as well, when you look at the prongs, you actually have a three-pronged plug. I'm looking at the plug head-on here. This prong here is typically called a grounding prong, a grounding plug. Basically, what I want is the voltage difference between the positive, the slightly larger end, and the slightly negative end, just to be a nice safety feature here in case the charges are sort of jumping. Instead of jumping positive and negative, it can also be grounded here. Just like a lightning rod can ground electrical energy that we don't want, can actually deviate out another pathway. That's just an added safety feature. So that's just in terms of plugs in general. I do want to just look at series and parallel just in a little bit more detail, and then we'll just work our way to a combined circuit here. What's not immediately obvious here is how does adding more resistors in series actually affect the total resistance, and as well for parallel. So just let me walk you through a simple example. I try to keep the numbers a little bit easier so we can walk through them a little more quickly. Let's start off here with the 9-volt battery. So that battery is supplying 9 joules of energy per coulomb that actually passes by. Let's start off here really simply here with just a 1 ohm resistor. Remember, when you're using Ohm's law, when you go V equals IR, you have to decide where you're doing Ohm's law. In this case here, my Ohm's law is applied to just a single resistor. I'm going to say, if I was at the bottom of the slide, by the time I get to the top of the slide, I've gained 9 volts. By the time I got back to the bottom, I had to have lost that voltage, converted that electrical energy into light energy. So if I do Ohm's law just on that single resistor, I'm going to have 9 volts worth. What is the current if the resistance is 1? Well, the current is going to be 9 amps. Technically speaking, that's the flow of charge. Oh, it's really freely. The positive charges can move at a speed of 9 amps. Or you can think of it, 9 cars travel out of the parking lot. Now, what if I increase that resistance? So let's take the same 9-volt battery, and this time let's put on a 1 ohm battery, and let's put on a 2 ohm battery. In that case there, same battery that's trying to push these charges out. Somehow charges are a little bit, they have some foresight. So they can actually foresee what's upcoming in front of them, and they can actually slow down to compensate for it. They know they're going to still pick up the same 9 volt from the battery. The slide is still equally tall, but they actually realize this time there's one easy patch and then there's a rougher patch. What's going to happen here is definitely the speed is going to be slower. That's what we intuitively would feel. Let's use our formula here. what equivalent resistance would this be? Well, for series, you just add up the two. What's a 1 plus 2? Well, in total, I would have walked our way through 3 ohms worth of resistance. If my socket was actually, a 9-volt battery trying to run through a 3 ohm resistor, what's Ohm's law say? So again, we use Ohm's law, V equals IR. I'm going to use it at that 3 ohm resistor. If I have 9 volts worth of push, and then my current is I, and I have 3 amps total, now the amperes is actually going to be 3. So again, our intuition was correct. We now know the speed at which the charges pass by is a little bit lower. Fine. We went from 9, we went to 3. So the conclusion out of this one here, adding more resistors decreases the total current. And you can imagine just using that just as an analogy. I know it's not quite the number of cars. You can actually say here, less cars come out of the battery. Realistically, the accurate way of interpreting it is, well, low resistance, my speed is 9. Higher resistance, my speed is lower. But we're just going to use this analogy of how many cars here. So if I have low resistance, 9 cars come out. If I have a bigger resistance, a longer rough patch here, there's actually less cars that come out. So it's like the cars actually can have some foresight. They know, oh, this path here is a little bit more difficult. I'd rather just stay in the battery. Oh, if you're crazy enough, sure, you guys can still go out. There's only 3 cars that go out. Again, technically a speed, but using this number of car analogy would actually help. Let's do exactly the same example with parallel circuits. So let's start off with our 9-volt battery. And let's start off here again with our let's make it a 3 ohm resistor this time, just make the numbers a little bit different. So that so far is just series. Again, when we decide to do Ohm's law, I have to decide where I'm doing Ohm's law. So I can go here, V is equal to IR. I'm going to have gained 9 volts going through the battery. I need to lose all that voltage before I get back down to the negative terminal here. So if I lose 9 volts, we just did this math here. What's the current if my resistance is 3? Well, my current is 3. Again, technically, the correct interpretation is my speed is 3. Let's now add another pathway in parallel here. Let's make that pathway here also harder. So let's say this is a 3 ohm resistor. That's my first resistor. Let's tack on a 30 ohm resistor. Why not? Right? So in the grand scheme of things here, we still have 9 volts worth of battery. Our slide is still equally tall. We talked about in yesterday's lesson here for parallel, they're going to have one path that's easy, one path that's harder. And what's going to happen here is most of the cars that arrive at the junction will go down the easy path. Some silly people will still go down the harder path here. The total current coming into the junction has to, this is I total, has to match up to the I1 and I2. Let's call it I1, I2. Let's do that equivalent resistance just for simplicity here. The formula is a little bit harder, so 1 over R total is supposed to be the 1 over R1 plus 1 over R2. So I'm just going to punch in the numbers. 1 over 3 plus 1 over 30. Again, just use your calculator for this. Decimals will save you. 1 over 3 plus 1 over 30. This gives you 0.367. That's not the total resistance. That's the reciprocal of the resistance. So I go 1 over that answer there. And this gives me here, the total resistance is now 2.7. I wish I had chosen numbers that were actually a little more dramatic. But what's surprising here is you'll notice, again, the generalization is so true. Adding more paths is easier, right? Because some cars can be deviated off this way, some cars go down this way, more cars, or you can say they go down faster going down the 3 ohm pathway here. But what I want to imply here is you'll notice if I swap out this parallel portion and I put in just one single resistor, this total resistance here is actually less. So total resistance decreases, we wrote this down yesterday, decreases with more paths. And just comparing the numbers here, you actually realize, wait a second, that total resistance is even less than even the easy path. How is that possible? Right? That's exactly what sort of Ohm's law is suggesting to you here. The more paths you take, even if you end up adding like a horrendous pathway, a 30 ohm pathway, really, really hard to travel through, because now the cars have a little bit more options. We can actually go and calculate the speed going down these pathways here, because now we have more options. We actually have a lower total resistance. If I then put it on my sort of thinking circuit here, if I can swap out that combination just with the 2.7 ohm resistor, I can do Ohm's law again. Again, the formula is easy. V is equal to IR. You just need to decide where you're using Ohm's law. 9 volts. What's the total current? If my total resistance has dropped, it's now 2.7. Now my total current, 9 divided by this 2.7 is equal to 3.3 amps. All right. So let's compare here. Well, before this second path was added, there were only a speed of 3 amps. So that's the speed at which I can go through this 3 ohm resistor. I've added a horrendous path, but because it's actually in parallel, the overall resistance has dropped. The overall resistance is like swapping this combination out for just a 2.7 ohm resistor. And because the overall resistance has dropped, we actually have the overall speed coming out of the battery actually a little bit faster. So we actually have 3.3 amps. You'll notice that that speed is faster. Again, intuitively, the more paths, the faster we can be. Or you can use the analogy, more cars are actually willing to come out of the battery, even when faced with 2 paths. My original path here, 3 ohms, but just having another alternative, another pathway, actually gives it a little bit more ease because now they can turn off in this junction. More cars will come out of the battery. They can come out in total a little bit faster. At this point here, let me introduce you our 2 devices in terms of actually measuring voltage, measuring current. One is called a voltmeter. So definitely that measures the voltage. For voltmeter, this one here has to be, so it measures volts, but this one here has to be hooked up in parallel. So let's say I didn't want to do all this work here. I just want to stick a voltmeter and I just want to sense how much voltage is each of these resistors themselves using. The voltmeter here will typically have sort of 2 leads. It'll have a positive end and a negative end. I'm going to have sort of alligator clips and wiring here. I can put my voltmeter at any 2 points on the circuit. So I can hook up my voltmeter. I'll do this on a virtual lab in just a second here. So I can hook up my voltmeter and I can figure out, well, what's the voltage across there? Oh, it's 9. If it says -9, it's just because I have my voltmeter in the opposite orientation. I can put this voltmeter here. Well, what's the voltage that this resistor uses or this resistor uses? Very useful, especially when we're dealing with combination circuits. Again, we'll see that in a second here. But for voltmeter, it has to be added in parallel. What a voltmeter does, the voltmeter by itself is actually something that has ridiculously high resistance. So the voltmeter by itself, the machinery inside, has a really high resistance. Because what the voltmeter is going to do, every time you add a circuit component, we're going to put a circle with a V for voltmeter. Every time you add a circuit component, some silly guys are always still going to take down the harder pathway. But what I want is I want to sample the voltage as if this voltmeter here wasn't here. So what I'm going to do here is, just like I sort of demoed here, I'm going to make this voltage some ridiculous resistance. Let's make it like 3 million ohms or 3 billion ohms. So sure, some of the current here will still be risk takers and travel down my voltage, but I'm going to have the majority of the current still go down here. As that current flows through the 3 ohms, I'm going to be able to do I times R to figure out how much voltage that resistor used, even if the voltmeter wasn't here. So the voltmeter by itself has to have ridiculously high resistance. It has to be added in parallel, and it can sample the voltage across any circuit component by itself. We can couple that here with what's called an ammeter. The ammeter, as the name suggests, the ammeter is actually going to measure the amperes. Amperes was actually a measure of current, so an ammeter. For an ammeter, it's going to measure the current for us here. This one here measures the current, but how you put it in the circuit, it has to be in series. It has to be exactly down the pathway that you want. This one here should not be in parallel. So let's say I have my parallel circuit again. For an ammeter here, you can just say circle A for ammeter. If I want to know how many cars are coming down just this pathway, as the cars themselves travel through the ammeter, I can take a reading of how many cars are passing through my tunnel that would then therefore pass through the 30 ohm resistor. Unlike a voltmeter, which has to have high resistance to not interfere, the ammeter here has to be designed with very, very low resistance. Why low resistance here is, if the ammeter by itself had some resistance, that's going to change the total resistance down this path. That's going to change how much total current decides to come out of the battery, and that's going to actually impact the circuit before you put in the ammeter. So for the ammeter here, it has to be low resistance, and it has to be put in series. So those two are going to be super useful. I'm just going to hint at a combination circuit. We'll deal with all the calculations, and then we're going to switch over to like a virtual simulation, and we can actually build one of these circuits. So let's end off here with a combination style circuit. You don't have to fully be just series or just parallel. Let's again keep the numbers fairly simple. Let's start off here with a 9-volt battery. We're going to have one part that's series. So let's make this here a 2 ohm resistor. Afterwards, it encounters a junction. So there's a turning off point. One of them here is now going to be a 1 ohm resistor. One of them here is going to be a 3 ohm resistor. And again, don't let distance confuse you here. It may look like, oh, this path here, if I cut down this path, it's a little bit easier than this path because it's a little bit shorter. Remember, the electrons are already all lined up along the wiring itself. Basically, if I push the person next to me, that signal going down what looks like longer wiring here won't really have any impact. So far, if you're going to, let's just think intuitively before we actually do the calculations. We know our battery is supplying a total of 9 volts. Kirchhoff's loop rule says, by the time I go down the pathway here, well, the cars are going to come out the positive end. Notice all the cars have to travel through here. So this part here is definitely in series. All the cars have to travel through that 2 ohm resistor. However, as they run into this junction, this turning off point here, some cars will actually travel down the 1 ohm path. Some cars will actually travel down the 3 ohm path. I would expect more cars would travel down the 1 ohm path. Again, less cars will travel down the harder path here. Remember, I'm using this very loosely analogy with number of cars. Realistically, I'm actually saying the speed at which the chargers can go. I'm actually getting more current. They can actually travel faster through an easy path, a little bit slower through a harder path. And by the time they end up forming the junction again, they're back to the beginning and they have to use up all 9 volts. These two here are now in parallel, which is now going to be a combination circuit. So let's just see if we can do this here. Usually, the first question you try to solve is, what is the total current coming out of the battery? So find the total current. Find out how many cars are willing to leave the parking lot. They have that foresight. They know what resistors are coming up, in what fashion, and what hooking up. So what we're going to do here is we're going to use our formulas. I'm going to deal with the parallel part first. I want to replace this to having 2 pathways, one with a 1, one with a 3. I want to swap it out with 1 total resistor. Because that part here is parallel, I'm going to use the parallel formula. 1 over RT equals 1 over R1 plus 1 over R2. If you want to be really like sort of good refractions here, for this case here, you could say 1 over RT. I could do a common denominator. I could say R2 plus R1 over R1 R2. See if you can do the math there for yourself. R total is actually going to be R1 R2 over R2 plus R1. But what you're going to find that only worked because we only had 2 resistors. So usually what I do is I totally ignore that. I totally just punch in the numbers if I know them, right? Why not? So instead of doing that pathway, you might see that on some formula sheets here. They basically just did common denominator. They did like times R2 times R2 times R1, and then basically added the 2. Flip the fraction. What I'm going to do is I'm just going to naturally just go straight to, well, if 1 over R total is equal to 1 over 1 plus 1 over 3, I would just do it as decimals because I find decimals are easy to take reciprocals of. 1 plus 1 over 3. I know it's 4 over 3, but I'm going to write it as 1.33. Keep that number in your calculator. The equivalent resistance across just this parallel part is 1 over 1.33. So that one there is going to be 0.75. Make sure you keep your answers to sort of 2 or 3 sig figs. So basically what I've said is I can swap out that combination of having 2 resistors, 1 a 1, 1 a 3. I can swap that out with just a single resistor that is actually a 0.75. And what you're going to find is now I've taken care of the parallel part. Now all this part here is actually in parallel. I'm going to then run through a 2, and I'm going to run through a 0.75. I'm going to do an equivalent resistance again. If I want to swap out that series part in part 2, the equivalent resistance is just going to be R1 plus R2. So in this case here, 2 plus my 0.75. I notice that the 0.75 is less resistance than both the 1 and the 3. By combining it, the total resistance is less. And now I swapped out this really confusing combination circuit. In fact, the total resistance is like having just one single resistor having a 2.75. So let's just try it out here. We're going to need to think about that equivalent circuit, and then we're going to come back to this picture. My equivalent circuit here says, what if I had a 9-volt battery? What if I was able to swap out all of this ugliness, the series and the parallel bit? If I want to switch it out for one single resistor, I did the parallel part first. I did the series part afterwards. This resistance here is actually 2.75. Because I have that 2.75, I can now find what's the total current. The total current coming off my simplified circuit is the same total current because I used the inherently behind the scenes there's some loop rule and current junction rule going into this here, but I'm just trying to figure out what that total current is. So I'm going to do Ohm's law. I want to do V is to IR. I'm going to use it right here. So V is equal to IR. if my only resistor has to use up all 9 volts, what's the current given my total resistance was 2.75? My total current is 9 divided by 2.75. This gives you here 3.3 amps. So that's the overall speed that these charges are going to leave. We're going to use the analogy of this is how many cars come into the parking lot. So now back to my original circuit. So now I have extra information. Pretty much once you know the total current, the whole problem falls apart. I'll just finish off this last part for you here. So we have a total speed of 3.3, or you think that 3.3 cars come out of it. The 3.3 in series technically runs into a 2 ohm resistor. Now this is back to our regular circuit. What we're going to do is we're going to try to do Ohm's law just at that position there. So we know V is equal to IR. Whenever you have 2 out of 3, you can find the missing one. So if I have all 3.3 cars multiplied by 2, this gives me 6.6 volts. So what it's saying here is whatever light bulb that is, that actually uses up 6.6 worth of the voltage that you have. Well, I had 9 volts in total. So what's going to happen here is because all the cars have to travel through it, all of the electrons, or all of these positrons flowing positive negative, all of them lose 6.6 there. How much leftover voltage? If I hooked up a voltmeter for telling you how much voltage is left going down these bottom paths here, well, that's easy. Kirchhoff's loop rule says, going from top to bottom, by the time you get back, I have to make sure I've lost all 9 volts. If I lost 6.6 volts here, I can actually figure out what's the voltage across these terminals here. 9 minus 6.6 gives you 2.4. So we have a 2.4 volts has to be lost through that bottom part here. And now I'm basically done. Because I have 2.4 volts, now I know I had one path that was a 1 ohm. Let me double check my numbers here. The other path here is actually a 3 ohm. I know just looking at the numbers, this is an easier pathway. This is a harder pathway. I would imagine more people go down this path, less people go down that path. I can actually figure out what is the current going down each of these paths because I know only electrons going down this path have to lose 2.4. The electrons that decide to go down the other path is 2.4. No electrons will actually make it down both paths directly. I can do Ohm's law at each of these parts separately. So V is equal to IR. If I'm supposed to lose my extra 2.4, what's the current down path 1? I'm going to call it I1. If the resistance is 1, well, the current is going to be 2.4 amps. I can do that same Ohm's law relationship for the other resistor. I'm expecting it's a harder pathway. So if I equally lose that same 2.4, and the current here, I don't know, I2, the resistance here is actually 3. As expected, it's tinier, 0.3 amps. So there we go. Right? So we've done Ohm's law, and we can actually even verify Kirchhoff's junction rule as well. It said the number of cars that arrive at any junction, they all have to be accounted for. Whatever goes down one path, they can't go down the other path as well. So I can actually just verify here, if I had I total coming in, the total number of cars here, they all passed by, they all lost a lot of voltage, but they all ultimately passed through that detour. I have 3.3 coming in. You'll notice in total, between the two of them, I notice looking like it's adding only up to 3.2 amps. That's just because of a little bit of rounding error. It's trying to tell you, well, because I have these two pathways, most of the cars, 2.4 of them actually go down this way. Actually, the speed is actually a little bit faster going down that way. It's a little bit slower going down the hard pathway. So that's sort of a combination circuit here. I just wanted to demonstrate to you one fully worked out example where you can use Ohm's law. Again, the trick for that part there is using Ohm's law with each circuit part individually. What I'm going to do for you here is I'm going to introduce to you our sort of virtual lab simulation. I'm going to rebuild the circuit here. We're going to actually throw on our voltmeter and our ammeter as well. We're going to see whether these numbers that we actually calculated are actually what we expect. So let me just flip over to the virtual lab here. Okay, so just let me introduce you to this virtual platform where we're going to be building our circuits from. I'll again post the link here under the resources section so you can play around with that there. We have a toolbox on the side here where we have a lot of different electrical equipment here. It's nice doing this virtually here because you can imagine in real life there's so much tinkering and so many things that can go wrong. Oh, my battery's dead, or the wire was frayed, or the contacts aren't good, things like that. At least you can see in this virtual simulation here what should happen. So I'm going to just demonstrate to you how you can build a circuit. I'm just going to pull, we know in a circuit we need to have a battery. You can play around with the orientation by dragging and moving these red circles here. Again, it's best if you can build your circuit diagram so they're 90 degrees, and that way you don't need to worry about sort of wires crossing each other, whatever. Later on, I know I'm going to be building a load, so maybe I want to build up a wire just going straight across. I'm going to pull up a wire here, drag it so that one end actually connects to the other end. So when it overlaps here, it'll basically make that contact. It'll like solder the wire there. And then again, you can just drag the other end here, and you can just drag and drop and pull the wires. Wires are nice here where you can actually, I need a longer wire. Again, I connect that point here. I can even drag it over to however long that I want it. Again, I'm pulling out many additional wires so that I can get the 90 degrees. If I don't actually use a separate wire, it just sort of starts pulling at an angle, and it starts getting a little more confusing. So let me just sort of start at building the circuit that we had. For us, we just had a resistor, right? A resistor could be a load. You do it in the exact same way. Connect one side, connect the other side. We did talk about how to read the color bands as well. For us, maybe just a little more interesting here. You saw me just click that and just click delete, and just remove that circuit component. I'm going to pull out a light bulb here. This is our load, so this is going to take the electrical energy from the electrons as they flow through and actually convert it, well, in this case here for light bulb, into light energy. The light bulb also has two contacts here, so you just want to drag it over, connect the one side, right? And then maybe you want to orient it the other way so you can see the light bulb a little bit better. They even animate for you here, sort of later on when the circuit is complete, the electrons actually flowing through here. So for us, we had the one light bulb here that was in series. Make sure when you're pulling the wire here that you connect to both sides of the light bulb. Sometimes you sort of short circuit it. If you accidentally connect this side here also to the other end, it's way easier just flowing directly through the wire and not going through the light bulb at all. So make sure you just connect to the opposite terminal. I'm going to introduce that junction here. The junction here is like a turning off point here. I'm just trying to keep everything as 90 degrees as I can so you can see it better, but you can just play around with it some more. I'm going to give you an assignment later on that lets you build your own circuit and actually see if you can play around with what are the unknowns and actually figure out what we get from here. So just in continuation of building our circuit here, so I have another light bulb. I'm just going to see if I can rotate that down. So that acts as my other resistance here. One last light bulb here. I'm just treating my loads there as my resistors. So these are the things that are going to be soaking up the voltage. And I'm just going to connect the remainder here. Connect that part. Connect the wiring. Again, it's only the wiring here. That's nice. You can drag it however long that you want. You'll notice that the electrons that are in here, they actually aren't flowing themselves until I actually complete the circuit. Until there's a complete cycle, nothing's going to happen. I'm going to throw on that switch here. The switch here is like a door. It's currently in the open position, so that means the circuit will be broken. The light bulbs will be off at this point here. I'm just going to connect the rest of this here. Right now, because this is essentially you've like cut a wire because there's no complete path. You notice that the electrons don't flow. You can just toggle this on and off by just clicking the button here. As I click it, it's actually going to demonstrate for us here the electrons. Electrons technically have negative charge here. The electron flow is really negative going from the negative terminal to the positive terminal. Again, unfortunately here, that was the electron flow. That's actually what's happening. We mentioned here, we thought it was actually positive charges. So we're going to call that the I that we've been using in Ohm's law here is always conventional current. That always points from positive to negative. So as labels there, see if we have any values, right? So you can actually see what it is. Great, it's already a 9-volt battery. If later on you need to change the voltage, you just click that circuit component. I can increase the voltage here, I can decrease the voltage, and it even animates for you the brightness of the bulb by sort of how large these yellow lines themselves are. So for us, either you drag and drop it, I think you can type it in. Let's just go back down to our 9-volt battery. You can also flip the terminal. So flipping the terminal, now we have basically negative 9 volts, and now the conventional current goes the opposite way. Right? You can flip it back and forth that way. For us, our resistor, let me just actually punch in our values. For the resistance, I'm going to click the resistor here. Hopefully I can go down to 2 ohms here. Perfect. So we had it down to 2 ohms. For the other one here, we have a 1 ohm. So let's go down to 1. Drag this down to 1 here. And then the other one here, it was a 3 ohm that we had calculated. So I'm just going to go back to that there. And it does animate in real time for you, sort of, is there any difference in brightness? We'll come back in tomorrow's lesson to talk about power to actually see what the brightness depends on. So what you can hopefully see here is if we deal with that conventional current, because there were no junctions in this beginning part here, this first part here is series to the first light bulb. every single car has to travel through it. The speed going through it here, you'll notice unless I pull out an actual multimeter or a reading tool, I can't actually sense it. So we talked about doing two tools here. One is a voltmeter. You may recognize this here. The voltmeter here has the two leads. Let's say I can test the voltage across the side, the negative lead. Sometimes we are tempted to say, oh, red is positive and black is negative. Okay, that's just for convenience. If I accidentally go, oh, let's say the black on the positive end of the battery and the red on this side here, it's just going to read for me negative. It just says, relatively speaking, by the time you get to the top, you would have actually gained voltage. I just had these terminals backwards. Remember, the voltage here is also a circuit component. This one here would have really high resistance. So if you imagine the parallel circuit and actually going through the voltmeter itself, this path is so undesirable that very few charges go through, that we can sort of sample the voltage without really messing up my reading here. In a similar way here, I can test the voltage. Let's do it the positive way here. It should be higher before the light bulb, a little bit lower after the light bulb. There we calculated for us, again, some rounding errors here. We had calculated to be 6.6 volts, give or take a little bit here. Remember for Kirchhoff's loop rule, every time I go around a cycle, I have to use up all the voltage. If I start off at this bottom part of the battery here, I gain the 9 volts going upwards. I'm going to lose 6.5 volts. When I hit this junction here, whether I go down this first path or the other path here, this one here is a complete loop, so I have to have used up 9 volts, or going down the other path here, also 9 volts. So what we did is we went 9 volts, you minus the, for us we were at 6.6, so if we did 6.55, let's just put the voltmeter here. Just remember, voltmeters have to be added in parallel. So just connect it across this, and that's just the leftover difference, so that by the time I get back to the battery, I've used up all the voltage. Because these are parallel pathways here, we can actually measure, oh, it's also 2.45 volts going down that battery. It's just that this resistance here is a little bit lower. It amounts to into more or less than a brighter light bulb here. You see that the conventional current actually flows a little bit quicker through there. On the other side here, a little bit slower. Adding parallel paths in general decreases the overall resistance. However, definitely the easier path, we would expect the charges can flow quicker. That's the correct interpretation. Or you can say more cars go down that pathway. Based on Kirchhoff's junction rule here, we can say, well, all the current coming into this here, as they run through the junction, if I don't get divvied off in this direction here, I will be divvied off in the other direction here. In fact, sometimes mathematically here, when we do Kirchhoff's loop rule, so far, like we've been doing loops with the battery, this pathway here uses 9 volt, the other pathway also uses 9 volt. You could also say that this, and what I'm highlighting here, is also a loop. So around this loop here, it also has to be sum of the voltage is equal to 0. So say I lose 2.45 volts going this way. As I go backtrack, it would have lost 2.45 falling downwards. That means I would have gained 2.45. If I gain 2.45, lose 2.45 here, in the net around the loop here, it's again 0. So again, a confirmation that the loop rule applied. So let me just get rid of this voltmeter here. I think just drag it to the side. I can pull out an ammeter. In the past, the ammeter was just this tool here. They're trying to represent to you here, because you don't have the parallel leads, this one here actually has to physically be in the circuit. So in the past, what we would need to do is we need to maybe delete the wire. We'd actually hook up the ammeter. The ammeter is something that has really low resistance, so that as the current basically goes through here, we can just sample how quickly the speed is. I'm just going to complete the circuit here, and there we go. We can tell. For us, we have 3.3. Again, give or take a little bit of rounding. We can see the speed at which they go through the series part here. Nowadays, I see they actually were a little bit clever. This is just for virtual simulation sake here. They pulled out another ammeter here, measures the current, and this one here, they actually just let you, assuming you've done that, assuming you broke the circuit and actually put it in series, they're actually being able to read the amperes. So 3.27 cars, or that's the speed. 3.27 get through the first one. As they get divvied out, oh, only 2.45. More cars go down this path. Less cars go down the other path here. That's a little bit misleading here, because you do need to remember an ammeter has really low resistance. I don't want to necessarily change the current in the circuit all that much, but I want it to be able to flow through, and I want to track how quickly the charges move in actually getting the amperes. So that one there is the ammeter. Nowadays we have what are called multimeters, where depending on the setting, you can get it to set, oh, I want to measure volts. So you just sort of dial it to that setting. Volts can come in many orders of magnitude. You can play around with the order of the times 10.